No way.
Okay, we begin having a look at clusters. This is on page 38 of the notebook. You should have seen over the night, the last few days, I sent you 2 videos for you to have a look at and be able to do the nuclear cycles in both cases. The reason why looking at clusters is important is because looking at clusters and the different types of clusters and plotting them on Hertzsprung diagrams has enabled us to get that information. How do we know that a star is going to die in a certain manner? And I was quite confident saying, well, if it's this size star, then this is what will happen to it. If it's this size star, it will supernova and so on. What evidence do we have for all this? And we have a look at clusters. So what are and why are clusters important? So let's have a look at them. Going forward. They should be able to go forward. And it's going to just pause, isn't it? There we go. I'm going back now. Rightio. Let's have a look at globular clusters. So what we need to be able to do with globular clusters is to just what are they, how many stars and so on. There's a table there in your book that you can now fill in. So what is a globular cluster? Well, a globular cluster is a cluster of stars. So firstly, understand what a cluster means. It's a group of stars. They are a very old group of stars. So here is a globular cluster called 47 TUC. And in this globular cluster, we have millions, sometimes hundreds of thousands to millions of stars. It's like a little mini galaxy. Okay? They are old stars. They are densely packed. And they are normally, well, not normally, they always nearly are, outside our galaxy. Outside our galaxy, there are a lot of little mini galaxies. When I say mini galaxies, they're like moons are to Jupiter. We know that there's probably hundreds of moons of Jupiter orbiting. But there are big moons and there are small moons. These are like moons for our galaxy. These are teensy-weensy little moons. Okay, we want to use the word moon. Obviously, we don't have moons. Okay, we don't call these moons. But these are little bundles of stars that are in orbit in the gravitational pull of our galaxy. That means, because they've got millions of stars in it, they're also quite large. There's hundreds of, sometimes, tens of thousands of millions. Sorry. Hundreds of thousands to millions of stars. They are old. They're left over we just know how old they are. They are quite old. And because they're old, most of their young stars, which are bright blue and big, have all died. So the brightest stars are red giants and they're on the way out. So let's just recap. They're old. That's the first thing we know about them. They're outside our galaxy and they are globular. The word globular just means they form a ball. Okay, so it's circular in shape. Okay, spherical in shape. They're large diameter. They're many millions of light years across. Well, not many millions, probably hundreds of thousands of light years across, probably whatever estimate. They are lots of stars. They are densely packed and because they're old, most of their young, bright blue stars have died. So they have a tendency to look more orangey. Now that's taken through a blue filter, that one there, so that's the reason why it looks more blue than it should look like orange. Okay, let's move on. Okay, there is the same globular cluster, that's TUC47, as it appears to the naked eye. So you can see it there as being quite orangey in colour because most of those blue stars have gone. Okay. There is just a picture of a globular cluster over here. Okay, I've forgotten what I call what globular cluster that was. And over here on the left is its Hertzsprung-Russell diagram. We've taken each of these stars that are in here and plotted them on a Hertzsprung-Russell diagram. And what do we notice? We notice a few things. So I'll just put the main sequence back on. The main sequence is there. Okay? But most of the stars are left there. Okay? We've got a few stars over here which are little, maybe they're just aberrations. They're not part of the normal. They're not normal to this cluster. But majority of stars end up in that shape there. What is missing? These stars up here. These are the B and the O and the A stars. The O and the B stars are no longer around. Why? They've died. If they're no longer around, okay, then they would have been formed when the cluster was first formed. But because this is an old cluster, we now know that these stars here have no longer, they're just not there anymore. They're gone. What is still left are lots of F, G, K and M stars. And remember, this part of the spectrum here gives a reddish tint. So this is orange stars here and red stars here. So we get a yellow to red colouring of all the stars. Okay? That's quite important. Let's have a look at the thing again. What else? What other feature can I see? Well, if this was where the main sequence was, there is a definite point where it's all turned off. We've got a little bend on our main sequence. So our main sequence shape, these are still on the main sequence, but these ones up here, they're in the throes of dying. Remember, a main sequence star is a normal star. They are fusing hydrogen into helium in their core. So these are all doing normal fusion. And because of that size, what type of fusion would we be expecting in those stars? What? Proton, good. PP. Okay, so these are all proton. The CNO ones up there, which are in the top big stars, the CNO cycle is a massively rapid process. Why it has to be so rapid is because that they are massive stars. The CNO process being so rapid uses fuel at a massive rate to support the weight, and once the fuel has run out, the star then collapses and dies. So that's the reason why these have all gone. We call this point here, where they've started to turn off, we call it the turn-off point. Okay? The main sequence turn-off point. And it's quite important to be able to distinguish between those. Okay, so let's just recap. What do we see on a globular cluster? This is just a typical globular cluster. We see the fact that there are no B and O and B stars and very little A stars left. We have a turn-off point, which is somewhere in the F and the G range. It could be anywhere along the main sequence, and when we get back to that, it'll be quite important. We still have stars which are main sequence, there they are, but a lot of the stars are dying, there they are. Dying stars are giant stars, stars that have swollen up and are about to either explode or shrink down to white dwarfs. Okay, are you happy with globular clusters? Okay, let's move on. Okay, now we mentioned the turn-off point, I mentioned a few moments ago. Here is a globular cluster called 6656 from the New Cambridge Catalogue, or whatever, the New Greenwich Catalogue, I think it is. And we can see the turn-off point, if the main sequence is along here, then the turn-off point would be around about here. I think there is a, I click one more time, there's the main sequence, and clicking again, I should be able to see the turn-off point. So, what do I know about this turn-off point? Well, the more age to the cluster, the older the cluster is, the more that the stars up this end have died. All these stars up here would have died. So as the turn-off point goes more into the G and the G, K and M stars, we know that this must be a really, really old cluster. If the turn-off point was higher, it would be a young cluster because we've only lost the O's. The O's go first and the B's die later, then the A's die later than that, then the F's die, and then the G's die, and so on. Okay. Excuse me. The next type of cluster is called the galactic cluster. They used to be called open clusters. I'm still putting it in here just in case you might read in textbooks or on sites their names. We call them galactic clusters because they actually exist within our own galaxy. And we've already done one specific galactic cluster, that was the Pleiades. Now, so here is our galaxy, pretending it's our galaxy, and inside this square down here you'll see that there are many little places that stars are being born. So galactic clusters are where stars get born. And if stars get born in these galactic clusters, they're all being formed in one cloud. And that means that they are normally quite young because they're younger than our galaxy. Whereas globular clusters were formed with our galaxy. So globular cluster is nearly as old as our galaxy. But galactic clusters are being formed right now. So they must be younger than the galaxy. So they are very, well, relatively young. When we say very young, we're talking about stars here. So that's, that could be 1 billion years old. But it's still young compared to other things. So they're relatively young. Okay? They form from gas clouds or nebula within our own galaxy, and therefore the gas cloud is not as large as these globular clusters, so therefore they have a small diameter. They are loosely packed because they're forming from a gas cloud, and as yet the gravity hasn't pulled them into a nice, really tight pack. They only have 1,000 stars or so in their cluster because they're from a smaller nebula, small gas cloud. And because they are really very young, we have blue stars. Okay, so when we have a look at them, we see mostly blue and sometimes very bright red stars which are on the verge of death. So the brightest stars are blue, and there are some very bright red stars, and they're the ones that are going to explode as supernovas. So these are the normal general traits of a galactic cluster. One more time. First thing we've got to remember about galactic clusters is that they are inside the galaxy. So they're inside the galactic disk. They're young because they have to have formed after our galaxy has formed. They are small diameter because they're forming from a gas cloud within our own galaxy. The Pleiades is an example of this. They only have in the thousands worth of stars, up to 10,000 in the cluster. Loosely packed, there's lots of gaps between them. And the brightest stars are blue, and there are some bright red stars in there as well. Are we okay with the difference? Okay. As you can see on the side, there's a nice picture of a galactic cluster. What's its name? Right, it's the Pleiades. It's one that we've been very familiar with. Okay, Japanese call it Subaru. Now, we can only see 9 with the naked eye, the 9 sisters or the 7 sisters in some places in the world. Obviously, there's 1,000 stars in this cluster. So using a telescope, we can plot about 1,000 stars. So using our Hertzsprung-Russell diagram, let's get a different colour for that, there is the main sequence. If you have a look at the main sequence, what do you notice are present? Nearly all of the stars are present. There are O, there are B, A, F, G, K and M stars present. So there's the turn-off point. So the turn-off point, only these stars up here, these stars in that little section there, just getting some colour, these stars here have started to die. So some of the big O stars are beginning to swell up, become red giants, and begin the process of exploding as a supernova to die off. Are we okay with those? So the turn-off point is quite high. So therefore, if it's a high turn-off point, what can we classify or say is the age of this cluster? It's relatively young. Okay. Going forward. Yeah. This is a composite Hertzsprung-Russell diagram which shows a lot of clusters around the place and their turn-off points. So having a look at the first ones up here, there is our main sequence. I'll just put the main sequence on in purple. That line there is the main sequence. And each of the time we do our clusters, this is the Persei cluster. There is its turn-off point. Okay? Here's the Pleiades. There is its turn-off point. Here is the M67. There is its turn-off. I'll get a different colour for that one. There is its turn-off point. Let's try another colour. I can't see that either. Yeah. Okay. Of the three, I have just done the Perseids, the Pleiades, and the M, which is orange, the M67. Which one is the oldest?
M67.
Right. Old clusters because the turn-off point is quite low. If we have a look at M67 alone, let's have a look at what stars still exist in it. So here is the M67 cluster. Okay, so there's the M67 cluster. We ignore all the rest of it. These stars up here, these ones here, they would be red giants. These stars down here would be red dwarfs. Now remember, a red dwarf is a main sequence star which is either a K or an M class. And these ones over here might be G class main sequence or G5 stars, GB stars. Okay. Where are all the bright big blue stars? Yeah, there were big blue stars, but they've since died and gone to heaven. Okay, or gone to ash. Okay. Rightio, are we okay with that? Now looking at the Persei, which is this one here. Okay, I'll just actually get forward here. I mean, there's the Persei's main sequence. Now the main sequence is all of this, so please realise the main sequence goes down here. So the turn-off point is here for the Persei cluster. What stars are present in the cluster? So we've still got red dwarfs. So the red dwarfs are down here. We have G, F and A class stars. We have a lot of blue stars, B stars up there. But most of the O's class stars are beginning to die. Okay. So we can see that this is quite a young cluster. It takes a few million years for each type of star to die. So having a look at this one here, on the way down here are the number of million years that are needed for those clusters to be starting that turn off. So stars which have a turn off up here are 10 to the power of 7, or 10 with 1, 2, 3, 4, 5, 6, 7 years old. A turn off at this point here means that cluster is 10 to the 10, which is 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 years old. Okay, and if we put some commas in to make that more readable, one thing about metricism did, it took commas away, so it's basically, so this is 100 billion Is it?
Yeah.
100 billion years old. Now, 100 billion years old, slightly a bit more than the universe itself, isn't it? Okay. So, if you probably take 100 billion years for that to get down to this level here. Okay? For a turn off. We aren't down there yet, are we? Okay. Okay. So, just to summarise, the turn-off point can tell us a lot about the cluster. The most important thing that can tell us about the cluster is its age. Okay? So as the turn-off point moves down, it's because stars move off the main sequence. Now, where is it? Now, this is an app which is able to plot the movement of a star as it leaves the main sequence. So let's have a look at what's going to happen. These are called evolutionary tracks. So firstly, let's select the size of our star. The size of our star is 1. So we're going to look at the sun. Let's see what the sun will do. How will the sun die? I'm going to put on ZAM. Now, we should have realised what ZAMS stands for. Zero age main sequence. So when a star is born, it's added to the main sequence. Now, we know the main sequence is a band of stars. So there is the main sequence, but we know that it's not a thin line. It's actually quite thick. And why is it thick? It's thick at one end and thinner at the bottom, is because stars, when they first get born, go to this edge. And then as they age, they start to lose a little bit of mass and a little bit of brightness and so on. So they're on their Hertzsprung-Russell diagram, they start to move. And if we were to plot them, they would have to fit somewhere in that thickness of that band. Okay, but when they are first born, they are plotted on the Hertzsprung-Russell diagram on this edge, the zero age main sequence edge. Okay. We can't see them move. Remember, this is a Hertzsprung-Russell diagram. It doesn't show them physically moving. It just shows how their brightness changes with time. Okay, so that's the first thing. I'm going to also put on the other edge of the main sequence called the terminal age, the TAM main sequence. Okay, that's the edge of the thickness on the other side, the terminal age main sequence. And what happens is our sun is born here and then will undergo this modulation. So let's just go through it. Just go through that one there, that's right. Down. And let's run it. Okay. Right. Now the sun stays for quite a large period of time on the main sequence. So as you can see, if you really, really zoom in here, we started at this point just there. And how much have we moved? And I'll tell you the time. Where's the time? The time is nearly 6,000 million years. So down here is where the time is being measured. It's also measuring the temperature, the surface temperature of our sun, which is at the moment 5.8 thousand Kelvin. So it's 5,800 Kelvin. Okay? So that's 600 million years, that's 6 billion years. Okay? That's where it approximately is at this moment. So it's slightly changed from when it was born. Okay? But not much. Okay? Look how much it's moved. Okay, let's keep an eye on where it's going to go. Okay, not moving anything, just stop there. Okay, we're now down to nearly 10 billion years. So it's 10 billion, okay, it's 9.7 thousand million, which is billion. We're on the edge of the sun's removal from being main sequence. At this point here, it's starting to getting hydrogen to burn in its core difficult. It's looking around for as much hydrogen as it possibly can. Notice what's happened to its temperature. It's dropped. Why should it drop? Because it's not producing as much. Yeah, as much. It's not fusing as much because it's struggling to find fuel. Okay. In a few more minutes, it's going to run out of. Well, in a few more minutes. In a few more years, it's going to run out of fuel, and it's going to start the next process of its life. Right. We're now at terminal age. We're at TAM. Okay? Our sun is about to die. Okay, there we go. It's 11 billion years, and it's dropped down to 5,400 Kelvin. So if you were standing on the surface of the Earth, you would see the sun as being significantly less bright. Okay? Less warm. But it's actually got brighter. And the reason why it's got brighter is the sun itself has shrunk. Okay? The sun being smaller, and even though it is much cooler, well, not much cooler, it's only about 500 Kelvin cooler, is that the surface area of the sun is quite small, so therefore it's still putting out a large amount of energy per metre squared. So it wouldn't look any brighter, but you'd feel it colder. Okay, the world would be cold, but not for long. Okay, next thing is going to happen. Okay, you're about to go, and it's going to happen quite rapidly. Rapidly. Right, we're about to do it. What's happening? Right, we're starting to swell. Okay, stop. Go back to that. Yeah. Right, let's go from here. Right, we've just seen our sun do something. Well, it's going to be fabulous if you would be there, but it's going to be very scary if you're here. Okay? What's happening? The sun is becoming a red giant. As it becomes a red giant, it will expand. Okay? Woo, it does a little bit of a loop there. Okay? Okay. It's going up in the Hertzsprung-Russell diagram. Means it becomes much more bright. Becomes massively much more brighter. Okay? Increases its energy output. Okay? But what's it got to do that? It starts fusing rapidly what things? Right, whatever's left. Okay, it's only got helium in its core. Okay? So we are going to rapidly start doing helium. Okay? Has it got some hydrogen to fuse as well? Yes, but not much. It's nearly no hydrogen at all. But is it going to do what? It's going to, it's taken how much time to get there? It's 11 billion years old when it started to die, and now it's at 12 billion years old. 1 billion years, and it's swollen up. Now, a red giant, our sun will swell up to engulf Mercury and Venus and probably us. So hopefully by then we've moved off. Okay. Rightio. Then what's it going to do? Okay. Very quickly, and look how small it is. Stop. Right. Let's do that last bit very, very, very quickly. Let's go up here again. Now remember, we're at this point here. Okay? I want you to see how quick the last stage of life is. Finally, our sun will not be able to fuse helium into other elements. Now, the first thing, we call this a triple alpha process, don't we? Okay, the fusion of helium into other things. So the first thing it fuses, helium tries to find 3 heliums, okay, and it goes into, how many protons would there be in this? Now there's 2 protons there, 2 protons there, 6 protons. What element has 6 protons? Carbon. So it is fusing helium into carbon. Then other helium tries to join in and fuse this carbon, and the next one up is oxygen. So we get oxygen. So our sun tries to fuse helium into carbon, helium into carbon, helium into carbon. When we start running out of helium, we start to fuse carbon with helium and start bashing those things together. But each of these gives us less and less energy until we cannot support the push out. Remember, a star has two massive balancing acts to do. The biggest balancing act is it wants to shrink in under what pressure? Gravitational pressure. It wants to shrink because it's just a big ball of gas. Okay, it's a massively heavy ball of gas. So what keeps it from shrinking? Right, the outward fusion pressure, sometimes called the hydrostatic fusion pressure. Now, if the red arrows and the pink arrows there do not equal each other, what will happen? Right, if orange is bigger than pink, it will expand, as it does with the red giant, because suddenly fusing all this helium, we go, out it goes. But if the pink is bigger than the orange, it shrinks. Have a look how quickly it's going to shrink at this point. There is not going to be enough fusion pressure outward. In fact, eventually, you can't fuse anything anymore. Ready? Running it. But running it now. Whee! Down it goes.
Oh, it's collapsed. It's dead.
The last stage, as it shrinks rapidly, is only going to be a few 100 million years. Okay? So it's taken about 12 billion years to get to this point up here. So from here to here is 12 billion years, and from here and down here is 1 billion years. What is happening here? This is a white dwarf. A white dwarf is a star that really isn't truly a star. It's just a very hot, compressed ball of gas, which has no fusion going on. It's very, very hot, okay, because it's white, but has no fusion, but it's so small, it's very, very deep. Okay? So that's what's happening to our sun. Are we okay with that? Now, it wouldn't matter if it's a sun which is slightly bigger than ours. Let's have a look at an evolutionary track. Let's have a look at this. This is the evolutionary track of a 5 times the mass of our star. So you can see over here it's 5 times. What does it do? Okay, it starts here at 0 age main sequence. It comes over here to terminal age main sequence. What's this part here? It's the red giant stage. And then what happens to that point from here to here? That's the collapse and white dwarf stage. Good. I'm just going to run it. Now remember, for our sun, that took 13 billion years all over. Okay? Now this is a star which is 5 times the mass of our sun. Okay? Do we expect this to be a shorter or a longer time? Shorter. Okay? So let's have a look at its radio. It's running through and down. All up, let's have a look at the time taken for this star. The time taken from birth to death is 140 million years. Ours took 13 billion years. Okay? This star here is probably an A, nearly a B star. Okay? Because it's about 5 times. I'd say more of an A class star. Okay, that's probably there. No, just A. Okay. So most of the middle types of stars, these ones, oh sorry, that's wrong, it's bigger, it's too big. Most of these stars here will all go the same way. The process is they stay on the main sequence for most of their life, about 90% of their life. Then they swell up and become a red giant, and then collapse very rapidly to become a white dwarf. Okay, now what happens if you've got a massive star?
We give us a 100
We're going to do a supernova. Okay. We're going to do a 15 times the mass of our star. This probably exceeds the limit that we need, okay, the Chandrasekhar limit, as it's called, and that limit will probably enable us to have a supernova. But you think, oh, it's going to be a big bang. No, it's not. Have a look at what happens. Okay. It's very boring. Remember, the massive collapse into the white dwarf is the most spectacular stage because our sun is going to expand into a red dwarf and shrink into a white dwarf. This here is just going to expand and then blow up. Okay. Okay. So let's run it. We're done. Let's try. You blinked. Stop again and let's reset it. Okay, cool. Remember, all of these simulations are running at the same speed, so you can see how quick it is. So it's starting here. Watch it, and ready to set, go, run. Okay. Right, so let's firstly have a look at the time. It's only taken 16.4 million years. Okay, so 16.4 million years is not even enough for the dinosaurs to evolve. Okay, it started here as a bright big. This is an O or a B, very large B star or a small O class star. It still spends about 90% of its life on the main sequence. This star here, because it's already very, very bright, even when it becomes a red giant, it doesn't really get any bigger. It just gets cooler and slightly bigger. But what it does is this. Over here, it goes backwards and forwards a few times. And that's its variable stage. Now remember, we've already done Seifert variables and so on. As it goes backwards, in this little section here, it moves backwards and forwards in its brightness. Okay? So when a Seifert is moving backwards and forwards in its brightness, we know that it's in this last part of its life where it's about to explode. Okay? Then in the last few moments of its life, it goes up to here. It really starts to swell to a very large star, and then there's no more outward pressure. The entire core starts to shrink in. As it does this, it collapses that core into one of two things. If it's only a very small star, this is not too big, it will collapse into a neutron star, which is down here. Or if it's a massive star like these little doodles over here, that will become a black hole. Okay. Yeah. So the evolutionary track is there to there to, so there's the main sequence. Okay, let's do it again. I'm going to go forward. Okay, let's do a 15 million star. Okay, this is a 50 times the mass of our star. Sorry, not 50 million, 50 times the mass of our star. Okay, I'll just do it step after step. Okay. Okay, we get to go. Come on, go. I'm going to run it. Okay. Okay, we're at the end of our main sequence life. Okay, we're about to supernova. And over there, down, done. Now, black holes do not appear on the Hertzsprung-Russell diagram. Why? Right, they have no luminosity, therefore they cannot be placed on. So therefore, remember, it's a temperature versus luminosity scattergram. Okay, so those are the ends of our star's life. Okay, happy with that?
Shall I like the last one?
Okay, we're fine. Where's the Have I stopped that recording?
The green light's on your headphones.
Yeah, that's.
Oh, she's not recording.
Yeah, I don't know.
Was it in the beginning?